All right, so this is a lecture for October 12th, 2017 for the Tuesday, Thursday morning section. Okay, so we finished fatigue in the last class, so we're going to talk about creep, which is another version of failure that a material can undergo, and then we'll get into phase diagrams. All right, so we ended the class with the fact that fatigue can cause a material to fail well below its actual yield strength. This is due to the fact that as you cycle it over many cycles, the cracks and the voids in the material start to expand due to the pressures being released and added again over and over again, and the material will eventually fail. Some materials, though, do have a endurance limit where anything below that limit will not fail as long as the stress is below that. But if the stress is high enough and it hits the line, that results in a failure. Okay, so things like certain types of steel basically will blunt out a lot of the voids so that they will almost have a self-repairing type of result. So if I stay below a certain stress, that material will not fail. But most materials, eventually, they will fail due to fatigue, such as this line below. This would be an example of aluminum. No matter what that yield stress is, if I put enough cycles on it, it will eventually reach the line and cause a failure. Okay, so that would be aluminum has no endurance limit, and steel does. Okay, so the whole idea is that cracks will grow incrementally. We're adding energy to the system when we put a force through a distance on a material. That energy has to be dissipated. Typically, that is dissipated through crack growth. Or the other way would be for the radius of curvature of the void to expand. That would dissipate the energy as well, and that would be a material that can self-repair. But in most cases, we get crack growth, which causes failure. Okay, so let's take a look at this. So we model this as the change in the length of the crack over the number of cycles gives us a change in the K constant. This K constant was the A over rho sub t to the square root, and this will also increase, will grow because the alpha, or the A, excuse me, the length is growing over time. So this is equivalent to a change in stress, which is related to the square root of the length of the crack, the change in the length of the crack. Okay, so we can model that, like I said before. There's a toughness value that can be defined for any material, KLC. That number is essentially constant, but it's the crack propagation that changes, and that's related inversely to the stress that the material can handle. And this says sigma c is the critical stress, so essentially is the yield stress that would cause failure. Okay, so what happens here is even though the K may be smaller than it was the material originally had, over time that will grow and the cracks will propagate. So the result we see from this equation is that there's a change in stress. The change in stress increases as the cracks in the material increase in length. And as the cracks get longer, this can be accelerated by increasing the loading frequency, which will end up increasing. Let's see if we find it here. All right, let's try this one. So due to fatigue, a material can eventually fail even if the cycle stress is below the yield stress of a material. Is that true or false? So we were talking about the fact that yes, fatigue causes the cracks and voids to grow, which increases the localized stress. Once that localized stress goes above the yield stress of the material, it can fail. So the overall stress being applied can be much lower than the yield stress, which means that a material will eventually fail even if the cycle stress is below the yield stress of the material. So that would be true. All right. So let's go on here. Okay, so creep is another form of force and stress that can be applied to material to cause failure. So with fatigue, you are cycling the stress, but with creep, you are applying a constant stress over a long period of time. And what happens here is the material begins to relax, trying to accommodate that stress. So if I pull on something or I bend something and I hold it, eventually the material will take that shape, and when I release it, it won't go back. So it stretches out. It has a strain that moves over time. So obviously if we do this pretty dynamically, the material will rebound, but if I do it for a long time, the material will deform, the crystals will change, and they'll assume that new shape. Okay, so that's creep. And if you do that for long enough, at a high enough stress, the material will pull apart and can fail, if the stress is high enough. So we model this as 3 ranges of creep. We have the primary, which is the start of the strain. The strain starts off kind of quickly and then it starts to slow down. You can see the slope here. Well, with respect to time. This is kind of a nonlinear section, typically not modeled because of the nonlinear aspects of it. And then at the end, we see a similar thing. The rate of creep increases again until it fractures over a smaller amount of time. This also is a nonlinear effect. But the majority of the creep response, I'd say 90 to 95% of the time, it has a very constant creep with respect to the time that occurs, right? So if I took this value here, the change in the strain over the change in time, that would be constant. Okay. So as an extra credit question, what is that called? What is this constant change in strain over time? What's another name for that? From the equation of a line, what would this triangular section be called? So if you send me that, the answer to that before midnight on Saturday, you can receive some extra credit. I will tell you later in the talk how to send it to me. You have to follow the correct the way to send it to me, otherwise you won't receive credit. I'll tell you that later in the talk. Okay, so secondary creep is what we like to model because it has this constant region. And this is where we estimate the sample's rupture time. Okay. So we can estimate it from this region. Okay. All right. So how does creep respond? Again, it uses the same equation we've used in the past, that if we increase the temperature of a material, its likelihood to creep or change length with constant stress increases exponentially. So we're using the exact same equation we've already used about 3 or 4 times in this class. This time it's the rate of strain, so deformation with respect to time. We have our K constant we've talked about. We have our stress exponentially changes with the inverse negative of the temperature. So again, there's an activation energy for creep. Again, a number you would either experimentally find or you would look up at a table. And you have the exponential corresponding to temperature. So what does that look like if we graphed it out? If we take the log, natural log of each side, we can get a straight line, right, which has a constant slope. So the word I just used may be useful for the question I asked previously. And as we see, as temperature increases, the amount of stress needed decreases dramatically, okay? Which means the strain increases dramatically with temperature. So you need less stress, you get more strain. That's what this equation says, right? Exponentially increase in strain. The other way to look at it, since this and temperature are on the same side, they're inversely proportional to each other. Okay. So if we want something to strain or fail in creep, if we heat it up, it'll it'll strain much quicker. Okay, so let's do an example of that. So again, instead of using the calculation, a lot of these materials have been tested for creep, different types of iron, different types of steel, alloys, and they create tables that essentially take the exponential result and graph it so that we can just read off the numbers that we're looking for with respect to temperature, rupture time, and stress. Okay, so this is an example of one of these graphs. This one is for iron, and this is the graph of stress. Stress is on the y-axis. On the left side, it's in megapascals. On the right side, it's psi. You'll see that a lot, especially when we get into other calculations, especially phase diagrams. You'll see different units on the two axes, just so that we can do easy conversions from one axis to another. And then on the x-axis, we have a constant, or a kind of an equation that solves for a constant that is related to how long it takes for a material to rupture and its temperature. And if you look at this graph in particular, is the temperature is in Kelvin and the time is in hours. Okay, so I have a question here. If we have a temperature of 800 degrees C and a stress of 20,000 psi, how long will it take to rupture? Okay, all right. So we have our prediction of creep. Do a calculation here. Okay, so let's put down our givens. We were given in the problem. This is an S590 iron. So that's basically talking about how it was processed and the type of impurities in it. We'll get into some of the numberings for alloys later in the class. We're given a x-axis that is related to temperature, 20 plus the log of the rupture, time to rupture, and that's in Kelvin hours, so that comes right from here. So that's our dependent variable. We'll plug in the psi on the y-axis, and we can determine the temperature and time from the x-axis. Okay. Temperature given was 800 degrees C, which is 1073 Kelvin, right? So I'm converting that over. We're given a stress of 20,000 psi. We don't have to convert this to megapascals because it's already labeled on the y-axis on the right side. The left side is megapascals, so it basically converts for us. Okay, I'm also going to add a second temperature. What if we change the temperature, drop at 50 degrees C, which is pretty minimal temperature drop for a metal? This would be equivalent to 1023 Kelvin. Okay, so as we should be able to predict, higher temperatures exponentially increase strain, which would decrease the time to rupture. So a small drop should exponentially increase the time to rupture. So let's do that calculation and see what we get. Okay, so the solution. Go ahead and move this up so we can see all our numbers and our graph. We have 20,000 psi. That's our given. We just need to look that up on the graph. So this is a log scale. We're going to see these log scales quite a bit from now on. Phase diagrams use them quite a bit as well. And a lot of the time temperature relationships we're going to talk about in class use log scales. So let's have a quick reminder of how these work. So they're based on powers of 10. So the first one would be from 1 to 10. Each hash mark would be a value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they get spaced much closer as you get closer to the next 10's value. So the next group, 10 to 100, we have to count by 10s instead of 1s. So it'd be 10, 20, 30, etc. Okay, so 20,000 psi. The units are in thousands already, so 10,000 would be pretty close. That's be our starting point. 20,000 would be the next hash mark. We go over until we hit the line, and then we drop straight down. This converts to our what's called the L value. The L value in this case is the relationship temperature 20 plus the log of the rupture time. That's in Kelvin hours. Okay. So L can vary with the different types of metals that you're using, so you need to make sure you understand what your x-axis is for whatever graph you're using, because this can vary with respect to the material that you're testing. So in this case, it's 20 plus the log of rupture time. So all we have to do, we have all the information we need to solve for the rupture time. And L is taken off of the x-axis, and it's the value of 24. Okay. So what we do is we take this, and then again, 24, look at the units, it's 10 to the third, so it's actually 24,000. Okay, so we're converting this number to an L, and that's what we use to solve. So we use our L value, 24,000, and that equals our known temperature, 1073, 20 plus the log of the rupture time. Okay, so with that, we can solve for the rupture time. When you do that, I get 233 hours. Okay, like I said, this is in hours, not seconds like diffusion. This is for 800 degrees C. And how long is 233 hours? 240 hours would be 10 days, so it's approximately 10 days. So at an elevated temperature, if you stress iron 20,000 psi, it'll rupture in 10 days. Okay, so that could be a problem. What happens if we drop the temperature? We're not dropping it very much, just 50 degrees. We're going down to 1023 Kelvin. The equation's the same, 20 plus the log of TR. We're applying the same stress, so our L value is still 24,000. And then we solve for TR again. So our second TR, call this TR1, this is TR2. Our second TR, just 50 degree drop in temperature, I get a much larger time. 2,890 hours. This is at 750 degrees C. And this is approximately, let's see, 2,400 would be 100 days. So this is probably about 120 days, approximately. So just 50 degrees decrease. Same stress being applied to the material. The material lasts at 12 times longer. Okay, so let's go on. All right, so I think now we're ready for phase diagrams. Yeah, all right, so we're moving on to chapter 9. Chapter 9. We're talking about phase diagrams. So this is how we determine creation of solid solutions. What temperatures we can create solid solutions. If we have too high or too low of a temperature, materials are going to have more tendency to dissolve into each other. If we add too much of material, we'll get a mixture. And again, if we heat that up, we can change when the mixture becomes a solid solution. So it's similar to what we've talked about before. If you're putting sugar into water, if you do that at room temperature, a lot of the sugar will drop to the bottom of the volume that you're created. But if you heat it up, you can dissolve more of the sugar. Same thing with metals. If we put in impurities like copper and nickel, we can increase the tendency for copper and nickel to interact by variations in temperature. Then obviously the ending result is if we heat it high enough, we'll melt it. So phase diagrams show us the melting points, the liquid phase, the solid phase, and the solid phases if things precipitate out into various regions. Okay. So we're going to be able to determine temperatures at which these occur, how many phases exist for a material over a temperature and concentration range. We're going to be able to determine the composition of each phase, and this basically means how much nickel versus copper, or how much of one metal versus another is in each phase. And then how much fraction of each phase. And this is, fraction would be the amount of each phase that exists, right? So you can have, say, 80% if you have like ice in glass of water, you could have 80% ice, 20% water. And then if you're adding impurities, you could have, say, 80% of the ice might have an impurity in it, but only 20% of the water might have an impurity in it. So that would be the composition of each phase, and the fraction would be the amount of ice versus water. Okay, so that's what we're going to go over. All right, so solution versus mixture. This is what phase diagrams help us to determine. A solution, like we said, is a single phase. You add an impurity or a solute to a solvent. They mix together and they have a single property if they mix, if they're miscible together. Whereas a mixture, if we put in one phase and another phase, they don't mix, we'll get the two separate phases. And the sugar water is a good example. If I put too much sugar in, I will still have sugar on the bottom of my volume, and I will also have water, a sugar water solution. So I have two phases. Okay, so there's limits. There's limits to the amount of each material we can add together, where they'll become a single phase solution versus when they separate out into two phases. Okay. So in this example, if I heat a material at 20 degrees, so this would be room temperature, and I add sugar. This graph shows me that I can add about 65, 63% sugar to water, and I will get a single phase. That single phase is listed by liquid solution. You'll always see this on the phase diagrams. You'll have either a Greek letter or a normal letter that tells you the number of phases. Okay, so if I stay less than 63 weight percent sugar, I will have a single phase of a sugar water, a sweet, syrupy material. If I go above that, I will separate out. I will have a sugary water phase, and I will also have pure sugar that separates out. And that's what this line shows here. I have the sugary water or syrup phase, and I have the solid sugar that did not dissolve. But what you can do with this system is if I heat it up from this point, if I heat it up to 60 degrees, what happens? The sugar that was separated out as a second phase has now dissolved into the liquid, and now I'm at the region where I have just one phase again. I'm only liquid. Okay, so we can control the different phases by temperature. And the important thing to remember on these graphs is you only move horizontally or vertically. You don't move diagonally. So you either set temperature constant and you vary the weight percent, or you set the weight percent constant and you vary the temperature. Okay, so that's how you move on a phase diagram. All right. So here's an example of types of phase diagrams, and this is important to understand the difference between these. So if we have a one component system, which say would be water, right? Water can go through three different phases, solid, liquid, and gas. This would be called a unary diagram. That means that we're talking about pure water. There's no impurities, there's nothing else added to it. There's no other component besides the water. So the unary diagram, una means one. It means the number of components, okay? Not the number of phases. Because a liquid phase diagram or a water phase diagram has three phases, solid, liquid, and gas. But the unary is the number of components, not the number of phases. Okay. So the one we're going to talk about the most in this class are binary diagrams, which would be two materials mixed together to create an alloy. So copper, nickel, carbon, iron, those are the ones that we're going to spend a lot of time on. So we're going to spend most of our time on binary diagrams. Again, these can have multiple phases. You can have 4, 5, up to 10, 15 different phases off these diagrams. But if it's two components, it's a binary diagram. Okay. 3 components or more would define complex alloys. And we need to understand what these look like, but we're not going to use them very much in class. So a 3-component phase diagram is called a ternary diagram. And in that case, it's a 3-dimensional diagram. They look pretty cool, actually. You have one component on the x-axis, and the y, you have the two components there, and then in the z direction you'll have your third component, and then you'll have a kind of a surface mapped phase diagram in 3 dimensions. So, well, again, we're usually when they create alloys that have more than 2 components, the second component is a very small amount, and they'll just basically add that amount and then redraw the phase diagram at that region, and then you'll use it for your analysis. So you can kind of turn a 3-component or ternary diagram into a binary diagram by holding one of the compositions constant. So that's usually how those work. So as long as we know how to read a binary diagram for sure, we can understand ternary and other more complex diagrams. Okay, so when you look at this, a unary diagram has temperature and pressure as its axes. Okay, whereas in a binary diagram, we're going to have composition and temperature. So what does that mean? What happens to pressure? Pressure is considered constant. Okay, so we're going to create a phase diagram for a constant pressure. So that is important to know as well. So in a way, even binary diagrams are 3-dimensional surface plots, because the other axis, the z-axis, should be pressure. Because what happens with phase diagrams between Flagstaff and Phoenix? There's a huge variation, 20% variation in atmospheric pressure. So the phase diagrams will shift. And we know that from water, right? Water usually boils at 212 degrees Fahrenheit, but here in Flagstaff it's more like 180 degrees. So you get variations in your phase diagram that you need to accommodate for. So if we see a phase diagram with temperature and composition, the automatic assumption is that it's at atmospheric pressure, unless we're told otherwise. Okay, so how do we visualize the different phases in alloys? So again, we're going to talk about binary diagrams. So we're going to have 2 components. They will be graphed on the x-axis as a weight percent. All right, so if I have, say, 50% aluminum, I can automatically calculate the amount of copper is also 50%. So I can always go back and forth between them, right? Because they have to add up to 100. So if aluminum is 80%, copper would be 20%. Okay. So one question for you that you can add to for extra credit is, what if I had 90% copper in my component? What percent aluminum would I have? Okay, so if you email me the answer to the previous question as well as this question, you have to follow this format. You have to send me an email. The subject line has to have the lecture number, lecture 13, and in the body of the email you just put the answers. So put the answer to the first one, hit return, and then write the answer to the second one. And again, the second question was, if I have 90% copper in my binary element compound, what percent of aluminum do I have? Okay, so do that. You must send it to me before midnight on Saturday. All right. So this, we can see the different phases that exist in alloys. So this is an actual SEM, electron microscope image of the grains. So these are the grains we've talked about before. This would be, say, a room of crystal grains. We have a hallway around the crystal grains, and then we have another room next to it. But here you can see there is a very distinct color difference between those. We have a very light gray, and we have a dark gray system. This is the 2 phases. So if we added up the area of all the gray phases, and then added up all the area of the dark gray black phases, we can get a fraction of the different phases, right? So the light gray phases look like they're probably about 50% of this picture, and then the black phases are another 50%. So that would be our weight fraction, 50-50. What we also can calculate from phase diagrams is the amount of copper and the amount of aluminum in each of these phases. Okay? So the lighter phases, this light gray, says that it's mostly beta. So what we're saying here is that the copper dominates this phase, and that gives it its light gray color. whereas in the darker ones, aluminum dominates. So it's more than 50% in these. And this is the composition. So we can calculate the composition of aluminum and copper in each phase, as well as the weight fraction, which is the amount of each color in the image. Okay, so we're going to go over that a little bit more as we go along. And then typically, phase diagrams, we will use Greek letters as shortcuts for the two materials. So alpha, beta, gamma, delta, all of these are used quite a bit because most alloys have multiple phases, and we define those by the Greek letters. But they typically correspond to one of the fractions of material. So alpha might mean mostly aluminum, beta might mean mostly copper, and then something like gamma might mean a combination of aluminum and copper if it's a multiple phase region. So we'll go into that as we go along, but we need to understand the Greek letters because it helps us define the phase regions that we see in our graphs. Okay, so we kind of already talked about this already. This is moving horizontally versus vertically on a graph to take something that is, say, two phases, liquid and solid. If we heat it up to about 60 degrees, we'll turn it into one phase. So the phase boundary is the region where we go from one to another. So if I hit this line and then move into the next phase by increasing temperature, I am now in a single liquid phase. But if I cool it back down to, say, 40, I will have two regions. But with this graph, I can actually calculate the amount of each of the phases and the amount of sugar and water that exists in each part. Okay, so we'll go into that here in a minute. All right, so I already talked about that. Let me fast forward through there. Okay, so let's look at the most simple phase diagram that we'll see for metals, and that's nickel and copper. The reason it's simple is because copper and nickel are completely soluble with each other. This is very rare, actually. Most alloys, there's only a small amount of one solute that we can add, to the solvent and still get a single phase. But with copper and nickel, they're miscible over the entire range from 0 to 100%. 100% nickel, 100% copper, 50%, anywhere in between, they're miscible. And this is because this is the Roth rules that we went over a few weeks ago. Their crystal structures are the same, their electronegativities are very similar, and the sizes of the atoms are very similar. So they can swap out with each other very easily. Okay, so let's look at the phase diagram for copper nickel. So this is a binary phase diagram because it has nickel and it also has copper. Okay, so always read the y-axis, or excuse me, the x-axis. It tells you from 0 to 100 that we're talking about weight percent nickel. How do I figure out weight percent copper? I can kind of write that down here. If I just flip the numbers 100% to 0, go in this direction, this would be the weight percent of copper, right? Because they always have to add up to 100. So if I have 80% nickel, I have 20% copper, 40% nickel, 60% copper. So at any point, I always know the weight percent of the other component because they're binary and both components have to add up to 100. So weight percent is on the x-axis, temperature is on the y. A lot of times you'll have Celsius on one side, and then maybe over here you'll have degrees Fahrenheit. So that is useful. And a lot of times the x-axis at the top will be the atomic percent. So we'll have weight percent and atomic percent. So we can convert those, like we talked about before. If you just multiply through by atomic weight, you can go back and forth between weight percent and atomic percent. A lot of times these graphs will convert those for you, which is kind of nice. All right. So what do we know from this graph? We know that there are two phases that exist. There's liquid and there's solid. Okay? The liquid is defined by an L. You'll see that a lot. Whenever something's melted, we call it the liquid phase. And in this case, there's only one phase. We call it alpha. It's the first phase letter. And then we have a region where both can exist at the same time. Part of our material is liquid, the other part is solid. Okay. So the number of phases is 2. There's just L and there's alpha, right? The phase regions, or phase fields, we usually call them regions, there's 3. There's the liquid region, there's the liquid and solid region, and there's the completely solid region. Okay. So 3 different phase regions, 2 different phases exist on this graph. So what's going on here? So it's got some interesting information we can get. My first question to you would be, what is the melting point of pure nickel? This is something you could easily get off of this graph. You could also get the melting point of pure copper, as well as the melting point of any mixture of the two. So pure nickel would be 100 weight percent nickel. We go over. Looks like the melting point of pure nickel is right about 1450 degrees Celsius. What about pure copper? Well, if we have 100% nickel, we have no copper. But if we have no nickel, we have 100% copper. So we do it from the other side of the x-axis. And we get right about, looks like about 1090. So the melting point of copper is about 1090, it looks like, degrees C. So what's going on in between? Obviously, if I pick something in the center and I heat it to about 1250 degrees, I'll be in a region where nickel is below its melting point, so it should still be solid, but I'm above the melting point of copper, so a lot of the copper is going to be liquid. But what we actually see is there is nickel that is forced to melt below its melting point because it is interacting with the copper. The copper is melted and it forces some of the nickel to melt. But as you might guess, there's going to be less nickel because nickel inherently doesn't want to melt yet. And then the other way happens as well. If I have a solid phase, some of the copper that wants to melt will be forced to stay solid because it's interacting with the nickel. And this is the components, the amount of each copper and nickel exist in each phase. So in the liquid phase, there's an amount of copper and an amount of nickel, and in the solid phase, there's an amount of copper and an amount of nickel, right? So we can calculate that. It's much easier to calculate when there's only one phase because you read it right off of the x-axis, and it tells you the weight percent, right? If I'm right here at, say, 1250 degrees, I know it's 80% nickel, 20% copper. If I'm over here at this temperature, it's 20% nickel, 80% copper. And if I heat this up, this original one, to 1500 degrees, I'm still at 80% nickel, 20% copper. But when I'm in the middle phase, it varies, right? Because some of the copper is pulled into the solid, most of the copper is in the liquid phase, and we can calculate that as well. Okay, so let's go on how to do that. Okay, so our phase diagram. Let me take a look here. So there's one definition I want to go through first before we start calculating weight fractions and things like that. And that's that nickel-copper phase diagrams are called isomorphous. Isomorphous means that you're completely soluble at any weight percent from 0 to 100. Okay, this is very rare. Like I said, copper and nickel they have very similar properties, so they are very miscible with each other, which means they're isomorphous. Most materials are not isomorphous. There are very specific ranges. If you put too much of one into the other, you're going to get two phases of solids. So isomorphous is pretty rare. Okay. So what are the rules for measuring weight fractions and compositions and temperatures off of phase diagrams? The first rule is if we know a temperature and an initial concentration, we can determine how many phases are present, right? So we move in the x direction and find the concentration. We move in the y direction and find the temperature. We put a point right there, and then we can see what phase region we're in. So we know the number of phases that exist as well as what region we're in. Okay. Second rule, if we know temperature and initial concentration, we can determine the composition of each phase. Okay. So we go with the concentration to a temperature. We can, if it's a single phase region, we can read the composition right off of the x-axis. But if it's in a dual phase region, we have to do a fractional conversion, and we'll go over that here in a minute. And the last rule is if we know a temperature and initial concentration, we can also determine the weight fraction of each phase. Okay? So the composition for, say, copper and nickel would be the weight percent copper, the weight percent of nickel. Whereas weight fraction would be the percentage, has no units, it's not weight percentage, it's a fraction. It would be the percentage of each phase that exists. So if we have a liquid and a solid phase, we can calculate the percent liquid and the percent solid. Right? And again, whenever you add these numbers up for binary diagrams, the weight percents have to equal 100%, and the phase percentages also have to equal 100%. Okay, let me just rewrite this. This would have units, 100 weight percent for composition, whereas weight fraction does not have units, it's a fraction. Okay, so that'll be important as you go along, because if you write those incorrectly, you will lose points on homeworks as well as tests. So you need to make sure you understand the difference. Okay, so what's happening in these phases? So we have this phase diagram. This is our copper-nickel phase diagram again. We're just looking at a small region. And you'll see this a lot with a lot of our phase diagrams. Is, say, copper and nickel is, carbon and iron is a good example. To make steel, there's a very small range of carbon that can be added to iron to create steel. So there's really no reason to show the entire phase diagram from 0 to 100. They only show a very small region because that's the only usable region. The other parts make unstable materials. So this is just kind of a zoom in on the copper nickel. We're only looking from 20 to about 60, or no, excuse me, 20 to about 55. Right, so you need to be able to read the spacing of the x-axis and the y-axis and understand the ranges that you're looking at. So we're only looking at a range from 1100 to about 1350 degrees and a weight fraction of nickel from 20 to 55. Okay, that's just so we can zoom in and see. So what's actually happening to the material? Let's start with the liquid phase. Okay, we've heated up to, in this case, we're at about 35 weight percent. Nickel. And if we heat it to 1300 degrees, the entire copper nickel is liquid. They're one phase, they're one liquid phase. If we looked at them, it'd be like looking at a cup of ice, or not a cup of ice, a cup of water. One phase, one water. It's our copper nickel solution. Okay. As we cool it, we hit the phase boundary. We're starting to create some solids inside of our liquid. So in this case, it would be like putting the cup of water in the refrigerator, or the freezer actually, and if we hit a certain temperature, ice starts to form. So what it starts to look like is, if I'm close to this line, I have some solids, but I still have mostly liquid. It looks like if I put some ice in a glass, just a little bit of ice, and I filled it with water, I would have the solid ice components floating around in my water. Okay. The difference is I'm not adding the ice separately, I'm creating the ice by cooling it. So I am starting to freeze parts of my liquid, but they freeze into little segments, and I still have a majority of liquid in that range. So if I look at this, I can see, if I go horizontally, I get an estimate of the amount of each phase, right? So if I'm just at the line, everything is still liquid. This length of line gives me the idea of that the entire phase of material is liquid. Okay. As I drop down, I'm still pretty close to the liquid temperature line, which means it should be mostly liquid and some solid, I still have a line horizontally that I can draw. And if I break it up into two components, these two components give me the weight fraction of each component, right? So I'm closer to the line. This is the longer line, so it's the kind of a lever rule. If you're on a teeter-totter and you want to balance between a tall person and a little kid, the little kid would have to move further away on the teeter-totter, and the adult would have to move further in, kind of like a moment arm to keep a balance. That's how we measure the amount of each one. So the length opposite to the liquid phase region is actually the amount of liquid, and then the smaller line here would be the amount of solid. Okay, so we can use that to calculate. And obviously as we get down and we hit the solid phase line, now we're at one single phase, we draw our line and it shows that 100% of the material is now solid. Okay, so we'll go into that here a little bit more in a second, and we'll do it here. All right, so here's our phase diagram. We've zoomed into a region, and we're going to look at a couple of points here. All right, so I'm going to create 3 points that we're going to look at. Let's see, actually 4 points. Okay, so let's take a look here. We have point A, point B. All right, we'll start with those two. And then we zoom in and you can see point B over here. I'm also going to add 2 more points. I'm going to add point D right here, and I'm going to add point C right here. So now we have 4 points. These 3, C, B, and D, we basically move just by changing the temperature of a set concentration, and we move to 3 different points and get 3 different results. Whereas A, we moved in the horizontal direction. Temperature was 1100 degrees, and we moved horizontally and changed the weight percent. So how would you change weight percent, right? Temperature is obvious, right? You heat it up, you get to a new temperature, you cool it down, you drop back down. Weight percent, you would have to add more components, right? You'd have to actually physically add more copper to your nickel or more nickel to your copper. And when can you do that? You can't do it when it's already solid. You'd have to melt the material, add more of the material till you get a different weight percent, and then cool it back down again. Okay? So when you move this way on a phase diagram, you were saying, you're basically picking, I have a material that's 60% nickel, I have a material that's 20% nickel. We're kind of ignoring the fact that to make that, we'd have to melt it, add more carbon, or excuse me, add more copper to get 60%. And obviously you can't subtract carbon, or I keep saying carbon, I mean copper. You can't subtract copper to get 20%, you would have to add more nickel to dilute down. So that would be done at the processing plant, and then you purchase the material. So phase diagrams, we assume that has all been done when we move from the weight percent values, right? But temperature is something we can control. We can take our material, 60% copper, and we can heat it up and down and change phases. Okay. All right, so let's go through these rules using this phase diagram. So the first rule, rule 1, was if we're given a temperature and an initial concentration. The initial concentration, like I said, is the metal that I purchased. It's known to have, say, 60% copper in it. That's not going to change. Okay, even if I change the temperature and I move into different phases, overall there's still 60% copper. The only thing that happens is some of the copper can move into one phase and less copper will move into the other phase, and that's what we're going to be calculating. But overall, it always adds up to the initial concentration, what you purchased from the vendor. Okay. So the first rule, given a temperature and initial concentration, we can determine the number of phases. All right, so let's use point A as our example. Point A, we are given a temperature, right? To get to point A, it has to be 1100 degrees. So temperature equals 1100 degrees Celsius. And our initial concentration, we can read that off of the graph at any time. That is our initial, right? That doesn't change. So our C naught is 60, and look at my x-axis, 60 weight percent nickel. So how much copper do I have? Subtract it from 100, 40 weight percent copper. You can always calculate the other component just by subtracting from 100. Okay, so how many phases exist here? So they're labeled here. I have alpha. This is alpha plus liquid, and this is liquid. Okay, so there's only one phase in this region. A is fully in that region, so our answer to that would be one phase. Okay, so the way we write that is the weight fraction of each phase. We call that W, and we write the phase Greek letter. So in this case, it's alpha. So the weight fraction of alpha would be 100% because there's only one phase, right? So the other phase that can exist on this phase diagram is liquid. What would be the weight percent of liquid at this temperature? Hopefully this isn't a trick question, because just like compositions, the weight fractions have to add up to 100. If I already have 100%, the liquid obviously has to be 0. And you can see that off the graph. We're well below the line of melting, therefore there is no liquid, therefore 0 would be our answer for the other phase. So if you have one phase, that weight fraction is automatically 100%. Okay. All right, so let's do point B. Okay, so I'm going to zoom in. Let's use this side. It's a little easier to see B on this bigger graph here. Okay. How many phases exist? Rule 1. We're in the alpha plus liquid region, which means we have 2 phases. And what is the initial concentration? Again, the initial concentration doesn't change. We always just go straight down, read it right off the graph. In this case, it's 35 weight percent nickel, which means there's also 65 weight percent copper. Okay, and what's the temperature? So we had to have a given temperature and initial concentration. We have the initial concentration. The temperature of B, just go horizontally, is at 1250 degrees C. So a known temperature, concentration, we can see the number of phases. So that's rule 1. Rule 2. Given a known temperature and initial concentration, we can determine the composition of each phase. Composition of each phase. So composition is weight percent of the material. In this case, copper and nickel. Okay. Whereas the amount of each phase is not a weight percent, and it's not related to the amount of nickel or copper. It's the amount of solid or liquid, and it's a fraction. Okay, so remember that. All right, so let's do point D. So we're given a temperature and concentration. Since point D is listed, we can get that. The temperature is 1300. Composition is the same as the other point, 35%. Let's write that down. So temperature equals 1300 degrees. Initial concentration is still 35 weight percent nickel, 65 weight percent copper. Okay. How many phases exist at this temperature? We're in the liquid phase region, so we have one phase. one phase. That phase is all liquid. So if we're going to do weight fraction, we do weight fraction of liquid equals 100%. The weight fraction of solid would be what? 100 minus 100 is 0. So there's no solid at this temperature. If that's the case, there's only one phase, then my initial concentration also equals the composition of the phase. So if it's all liquid, then the concentration or composition, you can use those interchangeably, concentration and composition, of the liquid would be 35 weight percent nickel, 65 weight percent copper. So the subscripts we use are important because they determine what phase we're in, what material we're talking about, and we can compare them that way. Okay. So let's do point C for rule 2. Point C, we're down here now. Looks like we're at about 12, say 12, or not 12, about 1160 degrees. Let's say 1170. So temperature is approximately 1170 degrees C. The initial concentration is still 35 weight percent nickel and 65 weight percent copper, right? How many phases exist? We're in the alpha phase. There's only one, so everything's solid. So we have one phase. That phase is alpha. Okay. So if that's the case, the weight fraction of liquid, weight fraction of solid. If we're completely in the solid phase, there's one phase, we have to have 100% of that phase, which means we have 0% of the other phase that exists. Okay. And again, the concentration, since there's one phase, is the same, but this time the concentration is in the alpha phase, and that would be 35 weight percent nickel, 65 weight percent copper. Okay. So let's look at B. Point B gets a little more complicated, but the math is actually very simple. What's going on at point B? We are in the dual phase region. We have liquid and solid that exists in this region. Okay. So let me write that down first. We're at a temperature, let me write the temperature real quick, sorry. Looks like about 1250. Temperature, 1250 degrees C. We have two phases, liquid and solid. Okay. Our initial concentration, like I said, is always the same. We bought this material at 35 weight percent nickel, 65 weight percent copper, and we're just changing the temperature. Okay. But how much of each of these materials exists in each of these phases? That's what we need to calculate. Okay. So since we have two phases, we have two concentrations. We have concentration alpha, and we have the concentration of the liquid. Okay. So this is really easy. When we have two phases, we just have to go horizontally until we reach the phase lines. Okay, so we're in the dual phase region. We go horizontally until we reach a phase boundary. The phase boundary here on the left is the liquid phase boundary. Phase boundary here on the right is the solid phase boundary. So to measure the composition, the amount of nickel and copper in each of these phases, we just go straight down from the phase boundary, and that gives us the value for each one, right? So if I go to the left, I hit the liquid. This is the concentration of nickel in the liquid. If I go to the right, to the solid line, this is the concentration of nickel in the solid. Okay, so what would those values be? Looks like about 32 here, and this looks like about 45. Let's say 44. Okay, so how would I write that? The solid phase was 44, so 44 weight percent nickel. How much copper do we have? 100 minus 44, 56 weight percent copper. Okay. The liquid line, we go to the right, or excuse me, to the left and then down, we get 32 weight percent nickel. How much copper do we have? 68 weight percent copper. So what does this mean? These values, again, the initial concentration, like I said, is always the same. So what we're seeing is there's a tendency for more nickel to be solid than its initial concentration, and less nickel to be liquid in this initial concentration. So this is just a fractional average. The weight fraction gives us the amount of each, and if we multiply the weight fraction by the concentration and add them together, we will get this number. Okay? So we have our composition or concentration of each. When we have that, it's always in weight fraction, and it has the element, the component that is added as part of the units. Okay? So there's our answer for that one. Then rule 3 was the weight fraction calculation. So let's do that one. Go back to black. Rule 3. If we have a given temperature and initial concentration, we can determine the weight fraction of each phase. Okay. So let's just do point B, because that's the only one that has multiple weight fractions. We already wrote out the weight fractions for C and D and A up here, right? This was, D was 100% liquid, 0% solid. C was 100% solid, 0% liquid. And then A was way up here. It was 100% solid, 0% liquid as well. Okay, so those are already calculated. One phase, you already know your weight fractions. For this, we need to use the lever rule that I talked about. So let's look at this line. I'll try to draw it in different colors here. So we have a distance from our point to the liquid phase line. We have a distance from our point to the solid phase line. Let me just kind of draw this off to the side. We have a line that looks something like, got the red, we have our point, and we have the green. Okay, and we have our phase boundaries on each side. Okay, this is what we use to calculate weight fraction, and it's the lever rule. Because basically, like sum of moments, if you want the liquid side, you use the opposite length. If you want the solid side, you use the other length. Okay. So what does this mean? At this point, is there more liquid or solid? Right. The liquid line is on the left. We use the line on the right, which is longer than the other line, which is the solid line. So that means that there's more liquid in this. Okay. So how do we calculate that? We need to know the composition values, the 32 and the 44, and we need to know our initial composition, the 35 that we were given for this material. If we have those numbers, we can calculate the lengths of the lines, right? So we just subtract the differences. Okay, so I would do that. So my numbers are 32, 35, and 44. If I want the weight fraction of the solid and the weight fraction of the liquid. Those are my two phases. What fractions do we have? Like I said, if I want solid, I have to use the line that starts from the liquid line to my point. It's across, it's opposite of the solid line. So to calculate that, I would take my initial concentration, subtract the concentration at the liquid line over the entire length of the line, right, which would be the solid minus the liquid. Okay, that would be taking the little region 35 minus 32 weight percent over the entire length of the line, which would be 44 minus 32. So this is what I'm doing here. I'm going to go back up here. The solid, I use the smaller line. The smaller line has a width 35 minus 32. And I'm comparing that to the entire length of the line, which is 44 minus 32. Okay. So I do the same thing for liquid. I have to flip them, right? I have to use the line that goes from the solid to my point to calculate the amount of liquid. Okay. That's the lever rule. So instead I start with C alpha, my solid concentration, subtract my C naught over the entire length of the line, which would be C alpha minus C liquid. Right. So I plug in those numbers. I get 44 is my alpha, 35 is my C naught, over the entire length of the line, 44 minus 32. Okay. And also remember, weight fraction of liquid plus weight fraction of solid must always equal 100%. Therefore, you really only have to calculate one of these, and then you can always just subtract from 100 to get the other one. Okay. Well, let's calculate these out. This one up here, I get 0.25, which is 25% weight fraction of alpha. This one I get obviously 0.75 or 75% weight fraction liquid. Okay. So at this given point, point B, which was at a temperature, what was it, 1250? 1250 degrees, and initial concentration of 35 weight percent nickel. Let me look at that real quick. You see that this length of line versus this one, the green line is 3 times longer, and it's opposite to the liquid line, which means it's the weight fraction of liquid. So the amount of liquid is 3 times more than the amount of solid, and that's what the weight fraction tells us. Okay, then again, like I said, if you have these numbers, weight fraction, and you have the compositions in each phase, if you multiply those together, you get a weighted average, which will give you your original concentration again. So if I take the concentration of the solid, multiply that by the weight fraction of the solid, plus the concentration of the liquid, the weight fraction of the liquid, I will get my C naught. Because C naught never changes, unless I melt the material and add more of another component, which is not really practical. So this always has to stay the same. It's just that we're moving copper and nickel into different phases at different locations. Okay, so if I put in my numbers, C alpha was 44 weight percent nickel. The weight fraction of alpha was 25. Plus my concentration of liquid, which was 32 weight percent. All right, I'm taking those right off of here, 44 and 32. And there's 75% liquid. If I multiply that through, I will get my C naught, which is 35 weight percent. Okay. All right, so let's go on to the next part here. All right, get this started again. Oops, why is it drawing? Thinks my finger is the. Okay, let me just move to the next one. Okay. So, why do we want to change the composition of nickel and copper across a range from 0 to 100%? Why do we want to do that? Well, this is called alloying. We're making solid solutions. We're strengthening the material, typically. But there's limits, and that's why we have to do these variations and create phase diagrams to determine what kind of properties we get from that. So if you read this graph, we have 100% copper or 0% nickel, 100% nickel, 0% copper. This is the tensile strength of the pure materials. Obviously, copper is very weak compared to nickel. It only has a tensile strength of about 220 megapascals, whereas nickel has a tensile strength of about 370. Okay, so I'm reading that off of here. What's interesting about alloys is instead of getting a kind of an average between the two materials' properties, we can actually get a synergistic result. Synergistic means greater than the sum of the two parts, right? So at certain concentrations, the interaction of the two materials is beneficial, and we get a tensile strength of almost 450. So we get about a 150% increase in nickel and an over 200% increase in copper strength alone. So this is why we want alloy materials. We can get some really cool properties, but it only happens at a very set region, about 60% nickel, 40% copper. We get a very strong material, much stronger than the individual parts. Okay, but again, as we increase strength, we always lose what? We always lose ductility. So the ductility of pure copper is about 55%. Ductility of pure nickel is about 50%. At the maximum strength of the two materials, about 60-40, the ductility drops to 30%. So we maximize strength, we always sacrifice ductility. Okay. All right, so here's the phase. This is the typical phase diagrams that we're going to see. They look kind of complicated, but they're really not that bad. They're just more phases. But all the rules we just used for copper nickel, where if we're in a multi-phase region, we go horizontally, find the boundaries, we can get our compositions, and we can calculate our weight fractions. So no matter how complicated the graphs look, all you have to do is find the point, the temperature, and the C naught that you started with, move horizontally until you hit phase boundaries, and you can do all your calculations. Okay? And you always stay within that region. Okay, so let's look at what we got here. All right, so let me draw this so you can see a little bit better. These are the phase boundaries for lead and tin. This is a lead-tin alloy. So these are what the phase boundaries look like. We're going from 0% lead or 0% tin or 100% lead, that's weight percent, to 100% tin or 0 weight percent lead. Okay, those are our two components. We want to determine that. They'll usually write them on the edges there. And we can figure out different aspects of this material. So the tin lead can be incorporated, and we get these different results. We get a region here called the alpha, and then we can always define the regions by their boundaries, right? So up here is the liquid region, and then we have beta over here. So there's three main phases, right? So our single phase regions are 3, and then we can determine the other ones. So if we move horizontally between regions, we can define the compositions in those regions. Okay, so in this case, this kind of shark tooth shaped region up here, we have alpha on one side, liquid on the other. That means this is an alpha plus liquid region. And over here we have a liquid plus beta region. So if we go horizontally, we have a liquid and a beta, so that is a two-phase region as well. And what would be the two regions down here? We have alpha on this side, beta on this side. This is the alpha plus beta region. Okay. So binary phase regions. How many do we have? We have 1, 2, 3. And what is the total number of regions on this graph? We have 1, 2, 3, 4, 5, 6, right? So the total number is 6. 3 of them are dual phase regions. and the other three are single phase regions. Okay. So from that we can determine if we're in the single phase regions, we can calculate weight fraction and composition automatically. This is 100% alpha, 100% liquid, 100% beta, and if we go straight down we can get our compositions. But if we're in the dual phase regions, we have to use our horizontal line connected between the two phase boundaries. We get our compositions from the phase boundaries and the weight fraction from the length of the line from our C naught. Okay. All right. So there's some interesting points here. In this case, alpha. So alpha is a single phase region. This is a solid solution. There's tin in there, but there's also lead in there, right? But there's just enough of each that it causes one phase, an alpha phase. Whereas in beta, there's tin and there's also lead, but they have one single phase. If I add too much or too little, I get two-phase region, the alpha plus beta region. But what is mostly occupying the alpha region? And we can read that right off of the graph. This is 0 to 100% tin. So in the alpha region, there is very little tin. So that means most of alpha region is lead. Okay? Whereas the beta region, we're near 100% tin. Beta is mostly tin. Okay? And then, just so you know, lead has the periodic table value Pb, and tin has the periodic table value Sn. Okay. Oh yeah, and there's another line. So we have an interesting region where you go from completely liquid to two solids automatically, right? This is the only point that happens. If we're at any other composition, we are going to cool the material. It's going to go to the liquid. Part of it's going to stay liquid, some's going to stay solid, and then it'll completely solidify. This is a unique point, has unique properties. It's called the eutectic point. You go from liquid to completely solid. Okay, and typically what you'll see is that happens at a much lower temperature than anywhere else on the graph. Okay, and we have a composition, CE, at which this occurs. Looks like it's just above 60%. And if you have 60% tin, 40 or 63% tin, 37% lead, you will get the lowest melting temperature, and it'll go from completely liquid to solid in a quick phase change. Okay, so again, let's look at what's occurring here, and then we'll finish up this lecture. Okay, so we went through this before. When you heat it up all the way to the completely liquid phase, you have your glass of water. You just have water, you just have the one phase. In this case, we have a tin lead water solution, one phase. As we cool it though, we go through, if we're in this region, we'll go through a liquid plus solid phase. We'll start seeing our ice cubes, right? We have our liquid, but parts of it start to turn into kind of floating icebergs or ice cubes in the ocean. And as we get further down, the ice cubes get bigger until they occupy the entire space. Okay. Then we'll hit a single phase region. Our ice cubes grow until they freeze the entire fluid. Okay. And then in the next region, we get precipitants. So this is kind of like the sugar liquid solution. Everything's balanced, everything's dissolved into a single solution, but as we cool it, some of the sugar starts to come out of solution and it precipitates. And with metals, you see that as precipitants within the crystals. Okay, so we're getting precipitants into the crystals. The crystals' shapes don't change; they still look the same, right? The rooms don't change, but we have different materials precipitating out inside of the room. In this case, the blue is mostly alpha, but the red is beta. So that's mostly tin-based precipitation coming out. Okay, so that's our two phases. So we had a single phase, but then as we cooled it, we forced some of the beta or mostly tin material to come out as a separate phase, separate crystal structure.